Hi, welcome to lecture 15, quantum field theory. And last time we talked about a regularization of integrals that are divergent, and we looked at the example of phi to the 4 theory and identified that the processes with one particle going to one particle, the propagation at the next to leading order or at the one loop order was divergent, and the amplitude for two particles going into two particles, where we had drawn the following diagram, was also divergent. So we found that a way with the cutoff and the momentum space regulator to regularize the diagrams, and now we said that we apply the Camel principle to do the renormalization of the theory such that it actually is sensical and we can extract predictions from the theory also at higher order than just the basic so-called tree-level order, which does not contain any loop diagrams. Let us begin by remembering that while we were using a Lagrangian to derive the interactions and to calculate the amplitudes, and we assumed that all the fields and quantities in this Lagrangian were independent of the regulator that we introduced. In fact, the quantities, the fields phi and the mass and the coupling constant, all the quantities will depend on the regulator that we introduce in the theory. So we might well define this Lagrangian, the bare Lagrangian, where all the quantities have dependence on the regulator. And now we define functions that contain in this Lagrangian all the dependence on the regulator lambda and the coupling constant little lambda, and factor them out. In this form, it is convenient to use this z factor to the power 1/2 in front of the field phi. This is also called the wave function renormalization parameter, and for the mass, the parameter is called the mass renormalization parameter, and the coupling renormalization parameter for lambda. So we can write the definitions like this, where the z's are called the renormalization parameters, and the only special term here is the wave function renormalization parameter. The others are pretty much called as the couplings themselves. And what we can do now is to try to make connection to the Lagrangian that wasn't dependent on the regulator explicitly. And how do we do that? Is by rewriting the Lagrangian, the bare Lagrangian with bare quantities that we have here. We have explicitly introduced the renormalization parameters as defined above, and now we can rewrite it again by adding and subtracting this L1 terms essentially. So we have L1 here, but we subtracted the way by adding this -1s to all of the terms over here. So we have this Lagrangian that we're basically using last time to derive the amplitudes, because and here the parameters are not dependent on the cutoff. The m and lambda are cutoff independent quantities, and we want to use this Lagrangian to calculate quantities, and they should be connected to physical observables. So this is the goal. But in order to achieve that, we have introduced this so-called renormalization parameters, and now also we have also an additional term in Lagrangian that looks like that, which contains the renormalization parameters. Another thing which we can do is to expand the renormalization parameters for small coupling constants lambda. So at leading order, they all equal to 1 plus some correction lambda times delta z m, delta z lambda, or delta z phi. Doing that, we can expand this expression here, and we get the following expression. We have L lambda L1, where we which is the Lagrangian with momentum independent quantities. And here we have all the quantities that depend on the regulator. So we have all these regularization terms, so all the regularization parameters expanded to leading order and lambda, and we have this contribution here to our interaction, to our theory. So that means that also our interactions get a new set of Feynman rules with this Lagrangian, which we can read off as, for example, lambda being the new Feynman rule, that contribution that comes from this regularization parameter, renormalization parameters, is this part here. We can directly read it off, that this is lambda times delta z lambda and 2 lambda times delta z phi. We can reconstruct these terms here, so they're directly connected and can be just read off. Those expressions here directly. And we get, for the propagator, we have to take into account that also the field with its momenta is playing a role, so we will not derive it explicitly, but we can we know that this propagator is related to the counter term, or to the Lagrangian with the renormalization parameters in such a way that we get the new numerator in the propagator, which contains the coupling strength lambda, the momentum exchanged, and these functions that are the renormalization parameters. Having this new set of Feynman rules, we can again compute the amplitudes for the one-to-one process here, for example. And this is the familiar divergence that goes to infinity when lambda goes to infinity from the last lecture. And the additional contribution to this is actually just the contributions from the propagator here, the leading contribution. And the diagram, the 2-to-2 process diagram, actually leads us to gives us a divergent term as we calculated, and we can read off this contribution here from the vertex. This is 2 lambda times delta zf times plus lambda delta z lambda. So having this contribution here allows us now to cancel this divergence by the appropriate choice of this regularization parameters. We see the same can be done here, and I will just show you what is this possible choice, or what is the choice for this procedure of the regularization parameters to have finite results. So a possible solution is setting the wave function renormalization to 0 and the mass and coupling constant renormalization parameters to those values, such that you see that explicitly they will cancel this here, and in this expression this is 0, but the contribution from here will cancel the contribution from there. So this is set up in such a way that we have exactly no divergence. All the divergent parts are dropping out of those diagrams, and we are good at one loop. And we said that all the other processes, like 3-to-3, will lead to finite loop integrals in the one loop irreducible representation of the expansion. So introducing this new set of regularization parameters, or so-called counter terms, allowed us to absorb the infinities, even though with lambda to infinity, the counter terms obviously, or the regularization parameters obviously also go to infinity, but it doesn't matter because they are cancelled by the contributions from the loop. So this is a very nice result, because we can now make actually calculations and predictions in the theory by also noticing that from the starting point where the bare quantities lambda, for example, here are written down in the bare Lagrangian, the physical lambda that is actually observed in the experiment has a functional dependence in connection to the bare quantity. So now performing an experiment, for example, a scattering of two particles to two particles, right, like P1, P2 scattering to Q1, Q2 momenta, allows us to calculate compare the prediction to the experiment and extract this coupling constant lambda, the physical coupling constant lambda, and fix it. Also, observations of the field quanta of this theory would allow us to measure the mass in an experiment. Fixing those two parameters completely defines the theory, and we can do higher order calculations, and all of the results will be sensical and made finite by this counterterm trick. We still, however, the theory does not predict any interaction strength. They are pure numbers, and just they have to be put in due to the observations of nature to match two basic observations, for example, in this theory, the interaction strength and the mass of the particle, and all the other processes that you might think of can be now computed. Now, the interesting situation here as well is that we could make the statement much more precise, but we unfortunately don't have the time for that. This is called the renormalization group, or the theory based on the so-called Kalan-Semanchuk equation, where this quantity here can be shown that to really depend on the energy, and the dependence will be very similar as taking this lambda 0, so taking this lambda 0 and taking the derivative with respect to the cutoff scale, for example, or so this is a related quantity that can be so this derivative with respect to the energy scale of the coupling parameter. Again, this can be made much more precise, but the basic idea is that all the couplings now, when we change the scales of the theory, will also be changing. This is called the running of the couplings and masses of quantum field theories, and this is a quite important process, in fact, and one can really formally derive that the independence of correlation functions requires certain conditions in between the different parameters. So we know exactly how they change from one energy scale to the other, and in this case, this change of the scale of this coupling with the scale, it's really related just to the coefficients of the coefficient of the divergence of the one loop contribution to the 2-to-2 interaction divergence. So from here we could already have the simplest version of our so-called beta function, which controls the scaling of this coupling with energy. But this is again a quite advanced topic, which we might cover at the end, but not we will not dive in this in it at the moment. Now, finally, as I said, theory can be used to make predictions about nature once we have fixed the two parameters lambda and m. Finally, we can ask the general question: which theories can be renormalized at all? And remember, we had again this general interaction for scalar fields. For real scalar fields, we could in principle write any n phi to the n interaction. And we will now do some general considerations. We know that each loop has 4 momenta, contributes 4 momenta, and each propagator has -2 momenta in the high energy limit. So we can define the degree of divergence of a diagram by multiplying the number of loops by 4 and subtracting the number of internal lines, which are propagators, multiplied by 2. So that will tell us whether the diagram diverges or not. So if we have a positive d, it will diverge. If it's a 0 and smaller, it will be finite. Now there are some general statements we can also make. Namely that the number of loops is equal to the number of internal lines minus the number of vertices of the diagram plus 1. And I will prove this statement in a second. So now for phi to the n theories, there are n lines for each vertex. Internal lines connect to two vertices, and external lines have only one vertex. So we can combine this into a statement that twice the number of internal lines plus the number of external lines is equal to number n for the phi to the n theory times the number of vertices. Combining now A, B, and C statements, A, B, and C, so we want to know what is the degree of divergence in general of a theory with phi to the n interactions. We now can write 4 times L So we write 4 times L minus 2NE. This is the degree of divergence. So it's actually, this line is redundant. So it's 4L minus 2NE. And we insert for L this what we found for or what I will prove, that this is equal to the number of internal lines minus the number of vertices plus 1 minus 2n, number 2 twice the number of the internal lines. And now we also can replace the number of internal lines by c. Yeah, that's equal to the number of vertices, n times the number of vertices minus the number of external lines divided by 2. And this expression then can be rewritten or simplified as n minus 4 times the number of vertices plus 4 minus the number of external lines. So we actually observe that for n smaller equal 4, the phi interactions that have only phi, well, one is quite rare, but yeah, maybe also 1, 2, or 3, 4 powers. Only diagrams with n smaller or equal to 4 external lines diverge. Yeah, so, and that means we can always map, or we have always enough counter terms. And so if we have diagrams that are have 4 or less external lines, they correspond to powers of phi that is 4 or less, phi to the 4, 3, 2, 5, 1. So this are the only terms that are, then they are always present in the theory. So we basically can say, whenever we have interactions that are of the order up to phi to the 4, we will have only divergences that can be mapped on terms inside the original Lagrangian, and we can always find counter terms for them. However, if we take phi to the 5, for example, there is no term. There will be terms that are not mapped again on. So there will be diagrams that are divergent at each order in loop expansions. There will be diagrams that are divergent that cannot be where the divergence cannot be absorbed in the term in the original theory. So basically, after this regularization procedure, there are not enough counter terms to perform the renormalization, to map the theory, basically the health theory in itself. Right? So that's a problem. And on the other hand, if we have only up to 4 particles participating in the interaction, we can always find the counter terms and map the theory again on itself, basically absorbing all the divergences. And for all number of external particles that is larger 4, we have enough propagators to cancel divergences or or counter terms to cancel divergent subdiagrams. So one example would be, for example, here, 3-to-3 interaction. So here the number of loops is 2, the number of external lines is actually 6. Why is it 5? No, it's 6. The number of external lines is wait 1 second. No, the number of internal lines is indeed 5 here. 1, 2, 3, 4, 5. Yes. So the degrees divergence is -2. So this loop is finite. And if we had like another diagram where we have divergent subdiagrams that seem divergence. However, we have counter term to cancel the subdivergence. So this diagram is again finite because this subdivergence is cancelled by a, for example, by the term that goes like d mu phi as d mu phi, or the m squared phi squared would be the term that cancels the divergence in this subdiagram. So this theory with phi to the 4 is healthy. And they're healthy and predictive since we only have to perform a finite number of measurements. On the other hand, if we had a phi to the 5 theory, like in an interaction of this type, where we have some sort of additional mass scale here, this theory is non-renormalizable, as at each point in perturbation theory we would have additional counter terms, new powers of phi basically are arising, and we would have to cure this divergences basically by hand by performing new experiments, so to say, new multi-particle scattering experiments, for example, to absorb terms of the phi with 6 or 7 powers and so on. So this is something that is not considered. This is something that is considered a non-renormalizable theory. So we would need infinitely, in principle, infinitely many counterterms for an infinite series. However, this theory still can be used as an effective theory at fixed loop order, as the operators, for example, phi to the 6 and higher, are suppressed by the scale m that is supposed to be much larger than the energy scale that we are looking at the theory, that we are studying the theory at the moment. So we basically could say, well, I'm satisfied with the result, but with only taking the operators 5 to the 5 or maybe 5 to the 6 as well into account, but not even calculating and getting counter terms, finding counter terms for higher order terms or for terms with a higher number of phi's. And as long as we are operating at energies that are well below the scales but with which this operator, as we know it is called irrelevant operator, is suppressed, the theory is still good and can make predictions. Similarly, for example, in terms of Newton gravity, let's say here the Newton law, if we do the force law and the dimensional analysis of the force law, we find that this has mass dimension 2. Yeah, this is the radius squared has mass dimension -2, so we have mass dimension 4, but the force also needs something, has to be of mass dimension 2. So the Newton coupling, in fact, has negative mass dimension, -2, same as we saw here, the coupling strength in front of this phi to the 6 or the phi to the 5 term have a negative mass dimension. They are divided by mass scales, and this is an indicator that the theory, in fact, is not renormalizable. We will have diagrams that are not mapping on themselves, but lead to new divergences, and this is the case for gravity. So gravity would be, in principle, an infinite series that we wouldn't know how to extract how to handle at arbitrarily high energies, but it's a perfectly good theory at low energies where we are staying well below the scale of the Planck scale, that is equal to 1 divided by when 1 divided by the Planck scale squared is equal to the Newton coupling. It's basically the definition of the Planck scale. So as long as we are well below that energy and look at processes well below that energy, we can pretty much forget about all the corrections, quantum corrections from gravity. Yes, so this is the way how effective theories are, protected from the high scale, even though they are not completely, let's say, self-sufficient, in a sense that we always need more and more experiments to measure things with better and better precision. But given that the new or given that the operators, the irrelevant operators, have suppression scales that are way above the interaction energies that we're studying, they are giving very good predictions nonetheless. So let me tell you finally, as promised, this argument to prove why this equation was true, about the relation of vertices and loops and internal particle numbers. So we can check it essentially by induction, saying for the v equal 1, number of vertices being equal to 1, number of external lines being equal to 0, and the loop number being equal to 0, we can plug it in and say, yes, 0 is equal to 0, minus 1 plus 1. Here, minus 1 is the number of vertices, and plus 1 is a part of the formula. So this formula holds for this set of parameters of one vertex, 0 external lines, 0 loops. And now we can add to an external line. So this just one vertex is essentially just external line with dot. It's one vertex. Now we can add to the external line of a diagram vertex, for example. So that would mean that the number of internal lines goes up by 1, and the number of vertices goes up by 1. If we had, for example, a diagram of this type, we add a vertex to an external line here, so we get one internal line more and one vertex more. So yes, this is one operation. We can also join two external lines and form a loop. So if we have this diagram as before here, we can join the external lines and we form a loop. So the number of internal lines goes up by 1 and the number of loops goes up by 1. Before we had one internal line, one loop, one vertex. And now we have two internal lines, two loops, one vertex. This operation leaves the n number of internal lines minus v minus the number of vertices plus 1 invariant. Same as this operation. This also leaves this combination number of internal lines minus number of vertices plus 1 invariant. And since we can basically construct any diagram by successfully applying those, either adding vertex to the external lines or connecting external lines into loops, we can essentially construct any diagram we want. And so this equation in general holds number of loops equal to number of internal lines minus vertex number plus 1. So that is it that we needed to prove. And so we basically learned why certain theories are renormalizable, what it means to be renormalizable, in the sense that we have enough counterterms to absorb all of the divergences and make a sensical theory where we only have to fix a finite amount of parameters by a finite amount of experiments, and now we can make predictions with the theory. Or in other words, if there are theories that are not non-renormalizable, where we would have to make new experiments and fix new parameters at each order in perturbation theory. However, at energies well below those operators that are making those theories non-renormalizable, those operators are, it seems almost accidentally, but in fact there are more deep reasons for that, but those operators are weak. And if we're looking at energies that are well below the suppression scale of those operators, we can still make very good predictions about nature and study nature very precisely. Also, in those theories that are not non-renormalizable, but are valid effective field theories.